All right, in this video I'm going to be talking about double integrals, and I'm going to start off just kind of on a computation level, and then I'm going to kind of mix in the meaning in the next couple of videos after that. Okay, so right now I'm going to show you just how to compute a double integral, kind of what are we even looking at here, and then I will show you how we would use a double integral to compute an area, and then I'll show you how we would use a double integral to compute a volume. And then later on we're going to use it for other things, and we'll look at different techniques of computing these double integrals, but for now we're going to keep it pretty straightforward. So kind of the question I want to start off with is that if k is a real number, what's an antiderivative for e to the kx with respect to x? And we know that, okay? You think, go over here, you do a little work. Okay, the antiderivative of e to the kx with respect to x, well, e to the thing is its own antiderivative, I suppose, provided the thing is linear. So it's going to be e to the kx, but I'm going to have to preemptively divide by k for the chain rule. Okay, and then we add a plus c. We're trying to find an antiderivative. And so then I would say, well, you've done some partial derivatives. What if we wanted to take the antiderivative of e to the y times x with respect to, I don't know, say y? What if we were interested in the antiderivative of e to the xy dy? Well, it'd be the same thing, right? It would be e to the xy divided by x for preparing for the chain rule. But when we take the derivative of this with respect to y, we're going to get x over x e to the xy. Okay? So this is kind of like, in a sense, partial antidifferentiation is what we're going to be looking at. So the next thing I want to talk about is, what if I had already a partial derivative and I was trying to recover the original? And now, in general, this is a much more nuanced question. Solving partial differential equations is like the huge big field of mathematics, and we're only going to briefly touch on it. But we will do some of that stuff at the end of this course. Once we're done computing our double integrals and doing our vector field analysis and all that stuff, we will go in and we'll solve some differential equations, because it's very satisfying to get these solutions. So the question is, what if I already knew the partial derivative? What if I knew that I had a function whose partial derivative was 2 times x times y? Okay. Well, if you think about it, how would I take the partial derivative and get 2xy? Probably x squared y, right? If I'm taking with respect to x. So, but what I'm saying is, okay, so this is fx. So f of x and y is going to be the antiderivative of fx, with respect to x. Okay, well, that's the antiderivative of 2xy dy. Now this is something that we can factor on, right? Y is constant. So I've got y times the antiderivative of 2x with respect to x. This is something we're very well versed in, right? This is going to be x squared plus c. Okay, now you might be like, wait a second, why didn't you distribute that y in there? What's going on? And okay, I'm actually proposing that this is not only just any real number, but any sort of expression that doesn't have x in it. Okay, so it's a constant function that depends on y only. Okay? If it had x's in it, its partial derivative with respect to x would have, something that would not get us back to 2xy. So I need this to be a constant function of y. And this is something that you can find, provided that you have enough, enough data points about your original function, but it can be somewhat difficult to find. And the actual finding of this is really kind of like the nature of the differential equations course, not what we're doing here in multivariable calculus. So what I'm saying is, this is something we don't really need to find this, because what we're mostly focused on right now is definite integrals, the things that are going to come back with a number. And so, why don't we start getting towards that? So speaking of definite integrals, what if I went in here and I just kind of gave some bounds here for x? As x ran from 1 up to 2y, what would happen? And, okay, well, it's just like, well, let's just see. We already did this, right? We know that this is going to get us x squared y plus, and maybe I'll leave this c of y. Okay, maybe I'll leave that here. And we're going to evaluate this as x runs from 1 to 2y. And what I'm going to do now is I'm going to plug in x equals 2y and x equals 1 and subtract. Okay? And this is x equals 2y, so 2y squared is going to be 4y to the 4, and 1 is 4y to the 5. plus, well, c of y. It doesn't have anything to plug in on x, right? That's my whole point, is that it only depends on y. Minus, okay, when I plug in 1, I'm going to have 1y, y plus c of y. And now, if you remember from AP Calculus, it's the exact same thing that happened with the plus c when we evaluated definite integrals in one variable, was that the c's kind of like killed each other off. And that's the same thing here. And so you won't see me carrying this thing around when I'm computing double integrals. But it is, if we're just interested in an antiderivative on that level. So really what this is going to be is this is going to be 4y to the 5 minus y. Okay? So this integral with respect to x is going to come back as something in terms of y. And so that's something. Not sure why we would be interested in that yet, but I think you will see in a minute. All right, here's another example, and what I'm going to do is I'm going to have you just run this yourself. Okay, so what you should do is you should pause the video, you should work this yourself, and then you should press play, and it'll just come up with the answer. All right, there you go. Okay, so you work it out, you get 3x squared minus 2x plus 1. And then the next thing I'm going to ask is, what if I showed you this? Like, what would you do? Okay, so okay, what if I came at you with this? You know, that's kind of a question. And actually, like that. Okay, what if I came at you with that? Okay, well, my bracket is not put in the right spot. Okay, here, you know, if you were just to look at that and there were brackets around this integral, and it's like I just did that integral, you could probably do this, right? Okay, so think about, you know, if we let y run from 1 to x, it's going to give us something in terms of x that we could definitely integrate with respect to x, right? So using the result of, you know, this whole thing in brackets is equivalent to this, using this word, I'm going to say that this is equal to the integral from 1 to 2 of 3x to the 2 minus 2x plus 1. It's like, thank you, this is very anti-differentiable. This is x to the 3 minus x to the 2 plus x as x runs from 1 to 2. And that's going to be 8 minus 4 plus 2 minus 1. Okay. And there it is, you've computed a double integral. Okay, so this is basically the technique. You start from the inside, you work your way out. You don't know what this means yet, but I figured we'd start with this because, you know, it'll be easier to understand the meaning of these integrals if we actually know how to compute them first. Okay, so this is how you double integrate.